Long ago in my previous career, and when I started out doing X-ray observations of black hole systems. And in the many years in between, things have got more and more interesting, more and more detail, and quite a few years ago when I did a variation of this talk long ago, I would say black holes exist, and we had enough observational evidence that black holes did actually exist, and I think they're going to need some light on me to see me. And just recently, a whole new way of looking at black holes have turned up, which is gravitational lensing. Now, so if you say you're an astronomer and you're in the pub, and one of the top questions, are there aliens? The origin of the universe and black holes, those are about the topics that turn up. Brittany Truebody, who organises Traz Astrofest, sent me an email saying, well, could you answer one of these sort of questions? And of course, I partly had a talk on black holes already, so I picked black holes. And of course, with the gravitational lens discovery, made it quite topical. So that means I'll probably have to do the origin of the universe next time. So they exist. I'll just start that out at the beginning. So what are they? Well, I'm an observationist, so I won't go into the theory. It's really, really weird. But what I'm more or less interested in is how you find them, how you characterize them. Now, gravity sucks. It basically weighs you down, and I'll hopefully get back to it. Scuba diving. You're in the water, it's nice, and you're buoyant, and you can float around, and you're nice and happy, and you get onto the boat. Gravity sucks. It's really, really hard work. The more mass in a planet or an object, the more gravity, more force it exerts. The closer you are to that mass, the higher the force, the higher the weight. Weight is actually the force of gravity. It's not actually the gravity, it's not actually it's roughly the force. The weight on our planet at our distance. So, if you're on a planet, big massive planet, with lots of mass in it, make it squish the planet a bit, it gets harder and harder to escape. So the more mass of the planet, the harder it is to escape. And so, one of the moons of Mars is Deimos, and you could get away from that, float around in the solar system if you got to a speed of 20 kilometres an hour, which is a good running jump. And on the moon, you need to get a rocket. On Earth, it's 40,000 kilometres an hour, once around the world in an hour. The circumference of the Earth is 40,000 kilometres. The orbit of the space station is 1.5 hours, so a little bit further out. Now, if you're trying to get away from the sun, you're getting up to 2 million kilometres an hour. Now, there's some stars. A white dwarf is a star like the sun, roughly the mass of the sun, squished down to about the size of the Earth. So you need a huge escape velocity. And usually around about this point, I've done this. So when I throw that up in the air, it's actually going into orbit. Throw it up in the air and go around the centre of the Earth and come back if the Earth wasn't there. You throw it up harder, give it more velocity, more force, it will go higher in the sky, and if you throw it fast enough, it will actually get away from the Earth completely, and that's what those speeds are. Now, another weird thing is a neutron star, very, very high, and a black hole, that speed is bigger than faster than the speed of light. Now, one of my favourite wacky scientists, who was really clever, Albert Einstein, you can do this basic maths, when you get around to doing that in the first or second year physics, you show that nothing can go faster than the speed of light. No material thing. So, black hole is black because you shine a light on it, the light goes into it, doesn't reflect, it just gets absorbed, it actually gets sucked in by the gravity, and even if there was a bright light down there, it's not coming out, so it's completely black. And of course, seeing nothing else can go faster than light, can escape. It's a hole, you can even, endless garbage bin. A garbage bin just gets a little bit more black. So, and there's a relationship between the mass of an object and the size, the distance away from that object where the escape velocity is greater than the speed of light. So if you squish the Earth down, it comes down to about that big, a big peanut. If you squish the Sun down to where it becomes a black hole, that radius is 3 kilometres, 6 kilometres diameter. So the Sun, a black hole Sun is 6 kilometres in diameter. And here is a few of those. Earth, 2 centimetres, sorry, about that big. Sun, 6 kilometres. 10 suns, 60 kilometres. 1,000 sun black hole would have a radius of about Mars. And the biggest ones out there, 19 suns across. And the huge one with 21 billion suns worth of mass is bigger than the solar system. And that's about the biggest size black hole we've found. And so black holes are really hard to find. They're harder to find than the black cat at night. You can clearly see the cat here. It's nearly completely black except for the white feet. Well, it's harder than finding a black cat in a coal mine with the light switched off. Now, has anybody got any ideas how you'd find a black cat in a coal mine with the light switched off? I had a couple of good suggestions.
Food.
Put out food. Here. And when the fish disappears, you know there's a cat in there, or something else. But and of course, infrared doesn't work because that's light emitting, and so you can't see it. In a coal mine, it would be fine for a black hole. You could have a background, and hopefully the silhouette would show up. Problem is, the silhouette of in the sky, black holes are like 60 kilometres across. The stars are very finely spaced. The chances of actually getting a black hole between you and a star is pretty slim. But it does happen every now and then. And then we use a fancy trick called gravitational lensing, where the gravity of the object in the middle acts like a lens and makes the star in the background, you guys are going to be the Earth, black hole here, and makes this object look brighter. And there's a little bit of a graphic here. That's the background image, and it gets bigger as, say, the black hole here in the foreground and the background star. Everything's moving around, so the alignments get better and worse as you go. So there's a couple of examples of this where we're pretty certain we found a black hole with this technique. Nice Hubble pictures showing it faint then bright, and you can, if it follows this nice up and down light curve, gets brighter then faded with this sort of shape, it's pretty certain to be a gravitational lens effect. And the neat thing about it, the longer this takes, generally the more massive the object doing the lensing. So you can use this technique to find stuff you can't see, have no hope of seeing. Black holes is a good one, neutron stars, white dwarfs, planets floating on their own. So, or the fish analogy, by their effects on the companion stars. So you could have a normal everyday star, like this one, and a black hole. Could be a white dwarf or a neutron star, but black holes would do black holes. And this is so close to that one that material is pulled off this star, and it doesn't quite go straight down the plug hole. it forms a disk of material. Because the whole thing is rotating, it forms a disk, and it's a nice flat disk. And I just knocked the microphone out. And so when it forms this disk, and because of friction, the stuff in the middle, the bits right in the inner edge, glow hot enough to emit X-rays. On the outside, it emits heat, and in between, light. So you can look for X-ray sources, because the only places where you can get X-ray sources this way is when you've got a very massive object there. So I'm talking about the same sort of X-rays as you go into the dentist or your doctor and they zap you and they find out where your bones are. And these are just a different type of light. So you have light, visible light, and you have heat. You know, a little bit of heat there I can feel. You have radio waves. Those are all longer wavelength, lower energy. The other way is ultraviolet, which gives you sunburn, and beyond that, X-rays and gamma rays. And these are shorter wavelength, higher frequency, higher energy. So you need fairly special techniques to find X-rays from stars. But when you do that, you do a survey and you find there's quite a few X-ray sources out there, and then you go and find the companion star, the star that matches that position, the X-ray source. And then you look to see whether it's a binary star or not, two things going around each other. Now, then you use the Doppler effect, and I think I will try and boost my sound here. And the Doppler effect, you have a few trains in Tasmania. As the train is coming towards you, the pitch of the whistle is higher, as it goes lower as it goes past you. So anything emitting waves, the pitch of those waves will be higher as it comes towards you and lower as it goes away from you. So if a star with a spectrum, and the trick with stars is they have these nice marker lines in them for where elements absorb just that wavelength. So it's a nice sharp feature, you can measure it very accurately. So when the star is going towards you, they get shifted to the blue, and going away from you, it gets shifted to the red. Towards and away. And halfway it's neutral. So you can tell something's going around in orbit by watching the Doppler effect. And over time you measure how the line shifts backwards and forwards. And the bigger that amplitude, the bigger the mass the star you're seeing is going around. And if you see two sets of lines, you can work out all the masses. Especially if they eclipse each other, you can work out everything in the system. But generally, the bigger the amplitude, the bigger the range from coming towards you and going away, the bigger that range, the bigger the mass that star is going around. So once again, you don't need to actually see the other companion star. So typically with black hole systems, you have a black hole which is 10 something solar masses, and another star which is 2 to 10 solar masses going round it, or the two of them going around like that round each other. Now, how do you make black holes? I'm talking about normal black holes. These are ones formed from stars. And a star like the Sun, it lives out its life pretty boringly, collapses out a gas cloud, and this is the 25 words or less version of stellar evolution, without all the maths and the hand waving. And it runs out of fuel in the middle. It's pushing hydrogens together to make helium, and that creates energy. That energy flowing out holds up the rest of the star. Now, the stars don't mix up with each other, and so it's got a limited supply right in the centre. When that supply runs out, the central part core collapses, it starts pushing heliums together, and this releases a lot more energy, and to get rid of that energy, the whole star puffs up into a red giant. Eventually that gets unstable, blows off the atmosphere, and you're left with the core, which becomes a thing called a neutron star about the size of the Earth, with the mass of the Sun. Normal star. Now a big massive star, they are generally larger. It goes through, runs out of helium, but the helium runs out. So it's got hydrogen going on the outside, helium going. Then inside that collapses, starting putting carbon, nitrogen, oxygens together. More energy comes out. And runs out of that, those fuel. Collapses again in the centre and starts pushing stuff together to make iron in the middle. Now iron is very, very stable. If you try pushing two ions together, it uses up more energy than it releases. If you try and break an iron atom up, like uranium fission reactions, it uses energy. So when the big massive star creates core about 1.5 times the mass of the Sun, or a bit more of iron in the middle, it's got no more energy supplies. So the energy generation in the middle switches off, star collapsing in on it, and then you can tell when people don't know exactly what's happening, and the theorists don't know, and the mathematical models, it bounces somehow, and the star explodes. Okay, watch for hand waving. Okay. In fact, they've actually done quite a bit better than that. They've got actually the computer simulations to bounce now. And so it blows the rest of the star, maybe 10 solar masses, out into the universe. This gets incorporated in the next generation of stars, and this is where all the heavy elements beyond iron gets made during that time when this supernova goes off. What can be left, that 1.5 solar masses of iron, can start collapsing and collapsing, and then the pressure of neutrons against neutrons comes in. I won't go into that, okay. I don't need to wave my arms around at this point, but I won't go into it. And you get a thing called a neutron star, which is 10, 15 kilometres across and has a mass of 1.5 times the mass of the Sun. Weird stuff. Now, if there's more mass than about that, there's no force, nuclear force, pushing against from one part of the nucleus to another that can hold up to support the mass, the weight. So it keeps collapsing, and it collapses and collapses below that limit where the light can't escape and becomes a black hole. So we found quite a lot of those black holes. There's a list of about 60 black holes. They still call them black hole candidates. It's a holdover from the old days rather than calling them black holes. You have to go through a pretty complicated set of observations to say, that's a 10 solar mass object we can't see any light from going around another 5 in a binary system with a 5 solar mass star or a 2 solar mass star. And we've got measurements that are good enough to say that's a black hole using the Doppler shift. And I also found them in the centre of galaxies. And it turns out that nearly every single galaxy, reasonable sized galaxy, has a black hole in the middle. Even our own galaxy, here's Sagittarius. It's a pretty rubbishy diagram, but the teapot shape, I have always extended out to that star to make the teapot, handle and a big spout, and off the steam here is the centre of the galaxy behind this dust lane, and then there's a cluster of stars. In the middle of that cluster is a big massive black hole. Here's a close-up of the cluster. And here is taken from data, a simulation showing orbits of stars around something in the middle. And Kepler's third law goes faster, and there's something in there. And you work out the mass, it's 4.5 million solar masses worth of stuff in there. So there's a black hole. You can do similar Doppler shift stuff for clusters. Now, globular clusters are really, really pretty objects to go see in the sky. Southern Hemisphere has two of the best ones. And any Tolkien fans in here? The Arkenstone. The description of the Arkenstone being all sparkling and things, like a globular cluster. Okay. So there's some link between how galaxies are formed and how the black hole's in the middle. Which came first, or is some sort of mix of the two? Now, this is actually a bit of a problem, because how do you go from 10 solar mass, roughly 60 solar mass, something like that, that you can get out of stars and make something millions of solar masses? How do you put together all the little star-sized ones to make a gigantic million mass one? Or are there some, or is one idea is that you have very dense clusters in the early universe, very massive stars. One goes off a supernova, collapses in a black hole, that triggers the others going off in a black hole, and all these individual black holes coalesce pretty quickly. You can get black holes coalescing as galaxies collide. But exactly how you get a billion mass black hole in the middle of a galaxy, you get the idea? Anybody who starts giving you an explanation to that, they're in the hand waving stage. So we found lots of black holes, 10 solar masses, a few, 3, 4, up to about 14 is the masses we found. We have lots going from 500,000 million to up to a billion solar mass black holes inside galaxies. How do you get from there to there? Are there anything in between? Now, I've thrown in a couple of other things in this thing. This is the sort of range at which masses of stars go from 10th of the solar mass out to maybe 250. The ones more massive than, say, 10 solar masses are very, very rare. And so to get any black holes out here beyond 10, 15, 20 solar masses is a very rare occurrence. And we haven't found any with the standard ways of doing it, looking at binary stars. We found a few stars alive and well, up to maybe 250 solar masses. But every single case where they find something over about 80 solar masses is argued about. There are some ideas, the theory people say, that if you have a star of just pure hydrogen helium with what was made in the beginning of the universe, you can get very massive stars that way. And there's some theory people that reckon that the early universe made black holes about this mass here, 100-ish. So what are the intermediate things? Are there intermediate black holes out there? Well, the X-ray people find some X-ray sources are very, very, very bright, a lot brighter than all the other normal X-ray sources, binary X-ray sources. And I'll skip this one, nice stuff. But you can actually use how material falls down onto a black hole to weigh its mass. And they found a few cases of black holes with masses in between the two. Not all that many. It's very tricky to measure these masses, and they're very rare. So you're looking in galaxies far, far away. So this is where gravitational wave comes in. Now, I sort of warned people here that gravity waves, and to some extent black holes, everything you see is an analogy to what really happens. So a gravity wave is not something that's sort of like a ripple on a water. It's actually the whole room changing dimensions by a tiny little bit. And of course inside the room you wouldn't be aware of it because your ruler is also changing a tiny little bit. So how to get round that? You use light. And I'll just show you these. See, I've turned up the sound. Sounds of two black holes merging. And you can get this as a ringtone if you like, okay? You get the idea. And so these guys in LIGO found not one but two, and they think they had a third one, but the statistics is not good enough. And that's a bit longer. And that is actually a little higher pitch than the actual pitch. So I'll go back a bit. I'm going to trip over that. Duck. So along here is time. And here is the frequency which space is wobbling. And starts out wobbling a fairly low frequency, 32 hertz. You can just hear that. And goes up to 250, which is quite reasonable sound. You can hear that fairly well. Areas go up to, depending on how bad they are, up to a few thousand. Dog can hear 20,000 hertz. So these are pretty low frequencies. So, and this comes about, this chirp comes about because there's two black holes and they're in close orbit around each other, and they're stirring up space-time, and that uses energy, and the energy comes from the orbit. So as these two orbit around each other, they create a wave in the fabric of space-time. It's like, no, any analogy is not right. It's like those sharks. They disturb the water, they push it up and down and away in the middle. So that uses energy. It comes out of the orbit. They spiral in. They get closer and closer. The speed of the orbit goes up and up and up until they come here and go boom, and then they settle down. So the initial increasing frequency is the two black holes spiraling towards each other, and the sort of blue at the end is them blobbing about. So when you move a mass, you move space-time around you, and the bigger the mass, the more you affect space-time. The analogies with tables with rubber sheets on it, you can imagine an object wobbling that, but it's not quite the same as that. So how do you detect this? People have been trying to find gravity waves 60, 80 years, roughly that long, and it requires some very fancy engineering and very fiddly physics. So what they do, these guys got two detectors, one down here in Louisiana and one up here in Washington State, and the two long tubes at right angles, and they're getting the air out of those tubes, and they've had to invent a very powerful laser, extremely shiny mirrors that don't wobble around, and they send laser beams up and down here. And this is your ruler. Light doesn't worry, it goes the same speed. So it'll take the same amount of time to go up the end and come back, no matter what orientation. But, and that's, so they actually send the beam, split it in two bits, and then they combine them in the middle. And so what happens is, when a gravity wave comes through, the length of one arm first gets squished and the other one gets lengthened, and then it goes back. And I'm doing this by leaning my body, but if a gravity wave came through, a giant one, and we were bouncing a laser backwards and forwards, we'd notice that that wall there would, this distance would say squish in a little bit, and that distance would squash out a bit, and then reverse as the wave went through. But if we just sitting here, use what gravity wave comes through, we wouldn't notice it because everything gets squished and stretched.
Are gravity waves coming all the time? Or
yes, there's gravitational waves all around the place. And these things, these are big gravity waves, and they're still smaller than that proton inside the inside of a nucleus. So it's absolutely tiny. In nuclear physics, there's a unit called the barn, which is 10 to the minus 15 of a metre. They say that's big as a barn to hit when nuclear physics is happening. This is smaller, a lot smaller than a barn. It's a fraction of a tiny fraction of a barn in nuclear physics. And any wave, and light waves are one example, gravity waves would be as well, but we talk about the light waves in this, they interfere. So I'll do my little, so if you have two waves going together in sync and you add them up, they'll double the amplitude. If you have the waves completely out of sync, one going up and one going down, they add up to nothing. So they set the length of these two arms, so the the light waves, too many waves around here, add up to 0 when they combine them again. When the length changes of the arms, one gets longer, one gets shorter, they start seeing light at the combining point. So they measure how bright that light gets and bright and fade. And you can do that. Fancy detectors nowadays can detect one photon at a time, one particle of light at a time. So you put a very fancy detector.
This isn't theoretical, they're actually observing this.
Sorry?
This isn't theoretical.
No, this is what they do.
They are actually observing this.
Yep. So they've got 2 cases, 2.5. And they're in the process of improving all their gear, so make it more sensitive still. So that's the basic physics of it. So the black hole, 2 candidates they found, they measure the mass of the individual black holes before they spiral in, because it's just orbital dynamics with general relativity thrown in. There's no just about it, but it's doable. And you don't need a lot of supercomputer power to do it. And they find black holes here, and I'll zoom in a bit on that. So 3 cases, this is the half case. 2 original black holes, final black hole. 2 original, final black holes. And this one's coming out about 20, 30, 40, 50, 60 solar masses. So we're starting to see black holes. The starting off ones are about the size we've already measured. The final one is a bit larger. Okay.
So the fact that they've only found that fewer number,
well,
does that suggest that just our testing equipment isn't good enough? Or is it that there aren't that many that are crashing into
well, that's the question at the moment.
Right.
How many are they? So you can work out what your sensitivity is, and now that you've made a detection, it's a lot easier to calculate that. And then you figure out what rate they should be, how many black hole, double binary black holes we know from astronomy, from stellar observations, how many there should be. And at the moment, there hasn't been enough observations to put any limits on it. So we don't know, from normal optical astronomy and X-ray astronomy, we don't know how many 20, 30 solar mass black holes there really should be. We can make a guesstimate, an upper limit. This is actually measuring how many of those black holes there are in the universe, and how many bigger 100 solar mass black holes there should be from those mergers. So they're about to increase their sensitivity. They've actually shut down and they're increasing the sensitivity. They're going to bring on other detectors, one in India, there's one in Japan, there's one in Italy, a couple up here. And with these, you get actually a direction, because the gravity wave arrives at different places at different times. And you use that to triangulate where the gravity waves come from. With only 2 detectors, you only get a stripe on the sky. But with a sort of triangle around the Earth, you get an okay position. I don't know how good they're going to be in the end. But the other thing that point out, with bigger black holes, bigger mass black holes, they're bigger, and so everything takes longer. And so to look for what's happening around the supermassive black holes, you need to go to lower frequency, and therefore you need a bigger detector than 4 kilometres. So to do that, you put it in space. And there is a program the Europeans have, 5 million kilometre triangle of detectors, lasers going between them, measuring the distance between the individual satellites. They've done a test run which worked really, really well. It actually worked better than they thought ahead of time. So this, because it's bigger, will be able to detect mergers of the black holes inside galaxies. And so this is a pretty full diagram, but here we have like LIGO, the terrestrial interferometer, detect, if they're really sensitive, rotating neutron stars, supernova, compact binaries, so binary black holes spiralling in together. Now, if you go to space, you start picking up objects falling into a black hole, a star mass black hole. And then you start seeing up here black holes, binary black holes forming bigger binary black holes inside the centre of galaxies. And using pulsars, which are neutron stars rotating slightly, you start detecting other things. You use the network of timing stations through the galaxy. Very sneaky. And there may be some way of picking up the original gravity waves from when the universe started up. So, oh yes. Who's seen Interstellar? Okay. The actual depiction of the black hole, a gargantuan, with its accretion disk around it and the glowing ring around it, is actually pretty good. These guys developed a new set of computer code to actually parallel process the ray tracing and to get this diagram. What's happening here, here's the disk, it actually glows that way, and so you're seeing the disk, the light from the disk in the background bent round the black hole makes a circle. So that actually simulation is actually pretty good at what you would see if you're in an orbit near a black hole. Their timing about the time dilation near a black hole is about right. The planets are all rubbish. So, see if this works.
And is that accretion disk, is that where the X-rays come from?
Yes. So the accretion disk, there's a lot of energy being released by stuff falling in here, the friction on the disk, so the X-rays come from the inside part of this disk. Some of the material doesn't go down the black hole, it gets thrown into jets. But, boom. Bye. Thank you very much. Right. And for those who saw the last talk, they are all different.
Yes, that's good. Any last questions?
Oh yeah, I think we've run out of tape there, so the questions are in incognito.
Yes, yes.
You said that they now think there's one in every galaxy in the
Really?
centre. Is that like literally in the centre or just towards the middle?
There's some cases where it's not really right in the centre, but these intermediate black hole ones are off-centre. So, but they are 50, 100, few hundred, few thousand solar masses. Some people think that they could be formed in binary pairs near the centre of the galaxy, interaction with other black holes and get thrown out. There are a few cases where the really massive black hole near the centre, but not exactly at the centre, I think. but it's pretty rare. So the black holes in the middle of galaxies are in the...
A fleet of battleships and moved all those electrons, and you just had the core atoms. You could fit a whole fleet of battleships into a pin.
Yeah, so you put the whole of the sun, which is... No, I've forgotten what it is. 400 times, a million something kilometres, down to the size of, for a neutron star, 15 kilometres across. So you squashed everything down into that size. So the space between the atoms is gone. It's just one big nucleus.
Questions, Stefan? Well, we've had the benefit of Stefan's career as a scientist, doctoral scientist, and it's shown, his knowledge of the topic is shown tonight. And the thing that's inspired me is that Stefan has been able to explain some quite complex
Scoot around the outside.
where necessary with a wave. And it's been entertaining. It's so fun, it's been informative, and it's been entertaining. Stefan, thanks very much. And we all